Welcome everyone to another one of our virtual CEGO seminars. I'm pleased to have you all here today. And I just want to let you know before we dig into the talk that everyone besides the speaker and host should have their camera off and stay muted. And if you have any questions, you can message them directly to me in the chat with the chat button at the bottom of the screen. And I think that's all the small details that we need. If you have any questions throughout, just message them to me. And so I'd like to turn it over to Dr. Mariotti to introduce our speaker. Thank you.
Hi all, I'm glad to introduce Dr. Mary Kate Rogener, which actually I met a long time ago, like in 2008. She was an undergrad at Boston University while I was a PhD student. And she's done some undergrad research with Wally Fulweiler, who was a LSU, I think, postdoc. So then Mary Kate did a PhD at UGA, but then most of research was in the shelf of Louisiana, and she has worked with Nancy and Brian Roberts from Lincoln, and that's what she's going to talk about. I think most of the talk. Then she was a Knaus Fellow 2019, and since then she's stuck with NOAA. She's worked as a contractor for NOAA for the National Center for Coastal Ocean Science. So we'll hear about pelagic denitrification and methane oxidation in the oxygen-depleted waters of the Louisiana-Texas Shelf. So please welcome virtually Dr. Mary Kate Rogener.
Thank you so much, Julio. And good morning, everyone in Central Time Zone. Good afternoon to everyone on the East Coast. I'm really happy to be here to talk to you about the work that I did during my PhD at the University of Georgia. So I'll be talking to you about pelagic denitrification and methane oxidation in the hypoxic zone along the Gulf of Mexico, which many of you, is right in your backyard. So first, we're going to start talking about the Gulf of Mexico. I really like this book by Jackie Davis, The Gulf, Making of an American Sea. A quote, "Every day in the Gulf is an environmental disaster originating from sources near and far." And the Gulf of Mexico is undergoing significant ecological changes due to human interactions. This includes oil and gas production, fertilizer inputs, land subsidence, and many others that I couldn't list on this slide. These human interactions lead to ecological changes on the coast, such as increased risk of oil spills, such as the Deepwater Horizon oil spill that occurred in 2010, as well as hypoxia and harmful algal blooms, hypoxia which occurs on a reoccurring basis in the summer, as well as most recently cyanobacteria harmful algal blooms that occurred last summer running along the coast of Mississippi. And so these interactions and adverse impacts result in changes to the biogeochemical nitrogen and methane cycling within this environment and all at most other environments as well. And so we're going to start by giving a brief introduction about eutrophication, brief because I know many of you are very familiar with eutrophication. And Nixon in 1995 described or defined eutrophication as the increase in the rate of supply of organic matter to an ecosystem. And I really like this definition because it describes eutrophication as a process, an ecosystem that's undergoing changes in trophic levels. Those changes primarily are caused by increased nutrients, which fuel productivity. The productivity falls to the benthos and then can lead to decreases in oxygen, hypoxic and anoxic conditions, increases in greenhouse gas production, loss of biodiversity, and food web alterations. And from the figure on the right, you can see how over the past few decades, our coastal ecosystems around the world are being increasingly plagued by hypoxia and anoxia. And so greenhouse gases, hypoxic and anoxic conditions promote the production of greenhouse gases such as nitrous oxide and methane. Nitrous oxide has a global warming potential 300 times that of CO2 and contributes to atmospheric ozone degradation. Methane has a global warming potential 28 times that of CO2, and the concentrations in the atmosphere continue to increase, which are shown on the figure on the right. And there are many contributing factors that lead to the production of nitrous oxide and methane. So I'm going to talk to you a little bit about the microbial processes that impact nitrous oxide production and cycling. There are many different microbial processes that can produce N2O, consume N2O, but for the sake of time and for this talk, I will be talking specifically about denitrification. So denitrification takes nitrate and utilizes organic matter to produce N2O, nitrous oxide, and then the nitrous oxide reductase enzyme takes nitrous oxide and produces CO2 and N2 gas. So this process takes a form of reactive nitrogen, so nitrate, which can fuel productivity and ultimately leads to producing N2 gas, which is biologically unavailable to around 99% of the organisms alive. However, the nitrous oxide reductase enzyme is pretty sensitive to different environmental parameters, so fluctuating oxygen concentrations, fluctuating sulfide concentrations can actually stop the nitrous oxide reductase enzyme, resulting in denitrification, stopping short and producing N2 gas. And I'd also like to point out that denitrification is an anaerobic process, primarily occurring at anoxic conditions. And then we can talk a little about microbial processes that impact methane cycling. So you have methane is produced by both biogenic and thermogenic sources. Biogenically, it's produced by a process called methanogenesis, which takes CO2 and hydrogen gas, producing methane and water. And this primarily occurs within the sediments. So you have anaerobic methanogenesis occurring within the sediments. And then when we look at methane consumption processes, you have methane oxidation, which utilizes oxygen or any other molecule or any other molecule with oxygen to oxidize methane, producing water and CO2. So while methane oxidation is producing a greenhouse gas, it's producing a much less potent greenhouse gas. So we like to call it as effectively acting as a biofilter, similar to denitrification. And so just understanding the ecological changes that are occurring in the Gulf of Mexico, as well as these different microbial processes, we wanted to look at basically a natural laboratory in the Gulf of Mexico. So the Gulf of Mexico River or the Mississippi River and Gulf of Mexico has low oxygen due to nutrients coming in from the Mississippi River watershed, which has a significant amount of farms and cities. So you have peak discharge in the spring, delivering significant nitrogen loads. Then you have stratification. So all that fresh water is coming in from the Mississippi River, meeting the saline salt water of the Gulf, acting as a hat. The nitrogen is fueling productivity in the surface water. That productivity is falling to the benthos, where it is then consumed, resulting in a low oxygen area ranging from 10,000 to 20,000 square kilometers in size, depending on the year. And Nancy goes out and samples this every year since 1985. And sometimes when she goes out, there have been hurricanes which have disrupted the reported size. However, hypoxic conditions typically reestablish within a couple of days after being oxygenated by weather systems. So our main questions were, how does low oxygen and increased nutrients affect denitrification, methane oxidation rates, and greenhouse gas emissions? So welcome to the dead zone. This is just a depiction of the sites that we sampled over 3 years, so 2013, 2015, and 2016. All of these sites were sampled at least at 2 depths. Some sites were sampled at 4 depths, depending on their oxygen concentration. So if they were more hypoxic, we would sample more depths just to get a better idea of the microbial processes and environmental parameters across from the surface all the way to the benthos. And I'm not going to go over the methods in too much of detail, just keeping time in mind. But if you have any questions, feel free to let me know, and I would be happy to answer them. But we effectively measured inorganic nutrients at all of these sites, dissolved gases. We measured denitrification rates in the water column using stable isotope 15 nitrate. We also measured methane oxidation rates using radioactive isotopes of tritiated methane. And what I'd like to also highlight is that these are the first reported water column denitrification rates to date. So that's very exciting. So we're going to jump right into the data. Let me just grab a drink of water. So these, and I apologize for the size of the text. This is bottom water potential denitrification and methane oxidation rates. You have across the rows, the top is 2013, middle is 2015, bottom is 2016. The right-hand column is methane oxidation in picomoles per liter per day. The left hand is potential denitrification in nanomoles per liter per day. The color denotions are warmer colors are higher rates and cooler colors are lower rates. And what we wanted to show with this figure is that rates are really variable, not only across the shelf, but also between the years. So there is significant variability all over, which we thought was really interesting. There's really no patterns that we could pull out from these data. And so just looking at these data a little more in depth, here we have denitrification and nitrous oxide trends. Potential denitrification is on the left-hand side, again, nanomoles per liter per day. Nitrous oxide is on the right-hand side in nanomoles per liter. We have the dotted line, which denotes oxygen below 63 micromolar, which is the hypoxic threshold. And then each of the years are characterized by different colors. In 2015, I had the unique opportunity to sample on 3 different cruises across the summer. So we had early July, late July, and August. I've highlighted those in red just so they stand out a little bit more. But what we are seeing across the depth is that we are seeing variable rates from the surface to the bottom, as well as concentrations that appear that they increase with depth, concentrations of gases. And then if we look at the same with methane oxidation and methane, you have methane oxidation rates again in picomoles per liter per day, methane in nanomoles per liter. Again, we are seeing very similar trends to denitrification, where we have variable rates and concentrations that increase with depth for methane. And what I want to point out is that this is not surprising for methane, just because methane is primarily produced by methanogenesis. Guanchao Zhang was a postdoc in Mandy's lab. He measured sedimentary methanogenesis at C6b in 2013, and those rates were hundreds of picomoles per centimeter cube per day, specifically at that site. So what we're seeing here is that the sediments are actually actively pumping out methane. Then that methane is staying below that hypoxic threshold due to stratification. Ultimately, will get burped out whenever a mixing event occurs. And due to the variability in the rates, as well as the gas concentrations, we wanted to kind of see if there was anything driving the rates as well as the other parameters. So here are some Kendall's tau correlations that we did for denitrification. So DNF is denitrification, MOX is methane oxidation. And what you can see is that all but nitrous oxide have a significant negative correlation with dissolved oxygen. And this suggests that microbial rates are influenced by oxygen concentration, which is not surprising for denitrification since it is primarily known as an anaerobic process, but it is somewhat surprising for methane oxidation given that methane oxidizers primarily like to use oxygen. However, in the presence of methane and low oxygen concentrations, they can use other sources. So whether that be nitrate, nitrite, sulfate, etc. So now that I have given you a fire hose worth of data for 3 years across the shelf, I really wanted to dive into a specific year that we kind of saw anomalous methane and methane oxidation results. So this is in 2016. So again, this is the same graph that you saw before, where you have methane oxidation on the left, methane concentrations on the right, much higher rates and concentrations in 2016, which are highlighted in the green boxes. The reason that the methane oxidation rates there. So they're on the figure is on a log scale. And the reason we had to use a log scale was to be able to even fit the 2016 rates on this figure. They were so much higher. And we really weren't able to figure out the drivers and what was causing this increase in 2016, but there are a few ideas that we have. So we're looking at the microbial community right now as we speak, but I don't have those data right now, but we have some ideas about the variations in riverine inputs. So this is discharge data from the USGS buoy right near Baton Rouge, discharge in meters cubed per second. It goes from January 2013 all the way to January of 2017. And the red squares are the sampling times when we were out on the cruise. And the big red box denotes the 2016 the 2016 year. And what you can see is that there's really high discharge rates early on in the year compared to previous years. 2016 compared to 2013 and 2015. And then we look at NOx. So NOx is nitrate plus nitrite in micromoles per liter of nitrogen. We're seeing pretty similar NOx concentrations across all the years. There's really nothing that stands out visually. And then when you look at the nitrogen load, so that's discharge times concentration, we're seeing that not just the timing of the load is higher in 2016, but the total load appears to be higher. And this causes, I guess, ramifications for potential stratification becoming more impactful earlier on. So you have stratification setting up earlier, severity of hypoxia becoming more of an issue earlier on in the year, more input of nutrients, higher levels of organic matter deposition, resulting in methane really being churned out of the sediments and fueling those higher methane oxidation rates. So just a quick summary of what we just went over. We determined denitrification, methane oxidation, and greenhouse gas concentrations across a spatial extent of the Louisiana-Texas Shelf for 3 years. The extent and severity of hypoxia on the Louisiana-Texas Shelf are heavily impacted by physical and chemical factors that vary on an interannual basis. The factors controlling the hypoxia result in alterations to the microbial rates, which also vary on an interannual basis. And like I said, in 2015, we were able to go out 3 separate times. And so we really wanted to investigate the microbial dynamics at one site over the duration of the entire summer. So in 2016, I had the unique opportunity to sample site C6c on 3 different cruises, 5 different times. The reason we focus on C6c is that Nancy has been sampling C6c since 1985, if not earlier, and this site has experienced a very high frequency of bottom water hypoxic conditions. And so here are the C6c Microbial Dynamics during the summer of 2015. Left-hand column, we have potential denitrification rates in nanomoles per liter per day. Right-hand, methane oxidation, picomoles per liter per day. And along the x-axis are all of the sampling dates. So we have July 4th, July 11th, July 30th, and August 20th at 6 a.m. and 6 p.m. And what we were able to see with these data is that both denitrification and MOX were significantly correlated with sampling date. So this suggests that as the summer progresses, both denitrification and methane oxidation rates increase, suggesting that a potential increase in hypoxia and severity of hypoxia as that hypoxic zone sets up over the summer leads to higher rates of both denitrification and methane oxidation. And so this really highlights that, we have seen rates that not only vary on an interannual basis throughout, but they also vary throughout the summer, as well as on a day-to-day basis. There are a lot of things that we don't fully know what's going on. We're trying to piece together, looking at the microbial community and getting a better idea of the other regulating biogeochemical factors that could cause change on such a rapid basis in this ecosystem. And so what we want to move on to next is looking at more of the greenhouse gas dynamics. So we have a unique data set that has 3 years worth of greenhouse gas concentrations and rates. And we really want to probe the relative importance of the removal processes such as MOX and denitrification versus the potential fluxes, atmospheric fluxes of methane oxidation and nitrous oxide. So we calculated the fluxes of both methane and nitrous oxide to the atmosphere using equations presented in Wanikoff et al. These equations utilized average global methane and nitrous oxide concentrations, average wind speed at the location. So we used the National Data Buoy Center buoy that was close by, as well as using the gas concentrations that we measured in the mixed layer. The mixed layer that we defined as less than 8 meters of water depth. And then the depth integrated methane oxidation and potential denitrification rates were calculated in order to determine if methane oxidation was a significant methane removal process and if denitrification was a potential source of nitrous oxide to the atmosphere. So here are the rates, and what we determined was that the hypoxic zone is a source of greenhouse gases to the atmosphere. We have each of the rates reported in micromoles per meter squared per day, average for each year. F-MOX is the depth integrated methane oxidation rate. F-methane is the calculated flux of methane to the atmosphere. F-DNF is the depth integrated denitrification rates, and N2O or nitrous oxide is the flux of nitrous oxide to the atmosphere. And what you can see here is that we do see pretty high fluxes of both nitrous oxide and methane to the atmosphere for all 3 years. And just to put some of these rates in context, the Baltic Sea hypoxic zone has a F-MOX rate, so a depth integrated MOX rate of 12 to 82 micromoles per meter squared per day, as well as a calculated methane flux of 2.5 to 31 micromoles per meter squared per day. And in 2008, the flux of nitrous oxide was modeled in the Gulf of Mexico hypoxic zone to range from 3.3 to 5.3 micromoles per meter squared per day. And then compare this to another hypoxic area, the Chesapeake Bay. The fluxes of N2O to the atmosphere range from 0.02 to 4.3 micromoles per meter squared per day. And then what talk is complete without a back of the envelope ecosystem scaling exercise? So we did some ecosystem scaling just to get a better idea of the amount of nitrogen and the amount of methane that both denitrification and methane oxidation are removing from the Gulf of Mexico hypoxic zone. So based on the depth integrated denitrification rates, which ranged from 12 to 8,623 micromoles per meter squared per day. So this is different from the table before because this is a range from a minimum to a maximum versus the average. We also took the average summertime duration and the aerial extent of hypoxia and determined that denitrification would remove between 1.7 times 10 to the minus 4 to 1.2 times 10 to the minus 1 teragrams of nitrogen per year. And if you scale this up even further, looking at the total end load coming in, we determined that water column denitrification would remove between 0.1 and 47% of the nitrogen loaded to the Gulf hypoxic zone. Again, as you saw, the rates were really variable across each year and across the entire shelf. This is a huge area, so it's not surprising that these results are such a big range. And then if we do the same thing for methane oxidation, so the depth integrated methane oxidation rates range from 7 nanomoles per meter squared per day to 474 micromoles per meter squared per day. Taking the summertime duration and aerial extent of hypoxia, methane oxidation will remove between 1.3 times 10 to the minus 7 to 9.0 times 10 to the minus 3 teragrams of methane per year. And unfortunately, due to the fact that we only measured methanogenesis at one point during this study, we couldn't effectively estimate the total methane load to the ecosystem, so we can't do the same percentage comparison that we did with denitrification. However, if you go back to the table and look at how we see a difference between the flux of methane to the atmosphere compared to the depth integrated MOX rates, the fluxes are so much higher for 2013 and 2015 compared to the depth integrated MOX rates. 2016 was kind of that anomalous year where we saw extremely high rates. However, due to the fact that we're seeing such a discrepancy between the flux of the atmosphere and the depth integrated rates, we've determined that more methane is escaping to the atmosphere than is being able to be consumed by methane oxidizing bacteria. So we're currently looking into seeing the regulating factors, trying to determine what is causing methane oxidizers to not be able to effectively consume all of the methane available. This could be due to a bunch of different factors, whether it be rare earth element limitation, trace metal limitation, etc. So our conclusions, water column denitrification and methane oxidation were variable, which is likely due to the oxygen concentrations, available nutrients, and physical processes, such as stratification, temperature, riverine discharge, residence time, etc. The impact of both denitrification and methane oxidation were low compared to the input of nitrogen and methane to the water column. And the hypoxic zone is a significant source of methane and nitrous oxide to the atmosphere. And it's important to understand microbial processes influencing these reactive gases as worldwide low oxygen zones are projected to spread. And determining the removal capacities and physiochemical factors impacting these processes would help establish a better understanding of the efficiency of biofilters and what it would take to maximize their metabolic functionality. So with that, I would like to thank all of the funding sources that helped support this work, as well as all of my co-authors who have worked tirelessly to help get this data published. And I will take any questions.
All right, thank you. So anyone who has questions, please send them directly to me and I'll facilitate the Q&A. Actually, I'll open up my own slide so we can record the questions that we do get. So I'll do that.
So I stop sharing?
Yeah, I think I might be able to share over you, so it probably won't be a big deal. All right. Test, test. There we go. So the captions are there. Okay, any questions, everyone? Okay, I guess maybe it's clear for everyone, or they're taking their time. I'm not sure. I thought it all seemed very clear to me too. I thought it was very well put together.
Thank you.
Good question.
Okay.
So this is very general, and because I don't know too much of this topic, but how much is so when I think about that zone, I'm thinking the concern is going to be on fishery, but here it seems that the major concern will be production of methane, which is a greenhouse gas, and so global warming. So how much is this aspect known to the scientific community? How much is emphasized compared to the other aspect, which again, it would be pretty much on fishery or locally the alteration of the ecosystem? How much is this the kind of the greenhouse gas known or put emphasis on? I really don't, I don't know. Mostly, I haven't never thought about the hypoxic zone as a problem, but for methane gas production.
Yeah, so I don't know if it's super widely known. I mean, there are reports, other hypoxic areas that are sources of methane and nitrous oxide. However, I think what is really important and what I like to highlight is that, we think of the hypoxic zone as a water quality issue. And what we're seeing here is that it's not only a water quality issue, but it's also leading to a potential atmospheric quality issue. So I think that's really important to highlight. Hopefully we can get the word out when we get these data published, but I mean, it's fairly well known that anoxic conditions will produce greenhouse gases, but of course, due to fisheries and the economic impact that fisheries have and all the people that rely on that, I can understand why the emphasis tends to be more on those areas.
Okay, so we have a question from Eugene Turner. The question is, would interpretation of the data be influenced much if the percent oxygen saturation were used instead of oxygen concentration? In other words, how sensitive are the critters to the saturation for what is out there?
That's a good question. I'm not exactly sure. I can look into that, and we can adjust the calculations to see if that would make a difference. From what we can tell is that we don't know how sensitive methanotrophs or methane oxidizing bacteria are to oxygen. It is fairly well reported that denitrifiers are pretty sensitive to any sort of oxygen fluctuation. However, due to the particle content, there are also reports that denitrifiers can do particle-associated denitrification. So it's really hard to tell exactly how sensitive they are to fluctuations in the saturation. But I will look into that.
Okay, so our next question is from Kendall Valentine Cole. Said, you have some of the first water column measurements of some nitrification processes or other biogeochemical processes. How did you get those first measurements?
So I think, we went out to my first year when I was a first year PhD student. I went out with Nancy and we sampled the hypoxic zone and we measured denitrification using stable isotope 15 nitrate, and it's pretty sensitive. Other people have used just the changes in concentrations, so they'll measure in a bottle, they'll have water samples in a bottle and they'll measure, the net change in nitrate over time, or the N2 argon ratio of the samples. But however, when you're using stable isotopes, you can really track where that isotope goes, and that's how we were able to see denitrification in an area where it really hasn't been investigated before outside of the sediments. And then for methane oxidation, previous studies have measured methane oxidation, but again, using the net change in methane. So you, again, incubate the samples, measure the initial methane concentration, incubate them for a certain amount of time, and then measure the final methane concentration. However, with tritiated methane, it has a really high specific activity. And so when you inject samples with tritiated methane, it doesn't enrich the system. So you're not over-enriching the system with methane, therefore stimulating methane oxidation. So we're able to really track the methane oxidation process pretty sensitively.
Robert Illes has a question. Do you think sampling at different times of day would have shown any significant differences in your results? You showed one slide with sample collections at 8 a.m. and 8 p.m. on one day in August, and the 2 times a day looked like they were showing large differences.
That is a really good question and has, I think, been on our mind for a long time, especially since we saw the data and the differences between the 2 times of day. I mean, there's a lot of changes that can occur, but our main takeaway from that was that the Gulf of Mexico hypoxic zone is just so dynamic. When I first started, you think of it as just like one big area with, the same thing going on, but changes can occur over time rapidly due to primary productivity occurring in the surface, enhanced respiration at night, especially at those sites where you have light that can penetrate to the bottom. We particularly targeted C6c because light can penetrate to the bottom, not a super high amount of light, but there is some PAR that was detected at depth. So I do think there is changes over the course of a day, which adds another complicating factor to trying to understand what exactly is going on and different shifts in the microbial processes.
Okay, any more questions? Still have some time. Okay, well, it looks like we don't have any more questions. So I just want to say thank you for this great talk. And I know you said that you're not doing any strategic work these days, but I hope to see some more stuff from you at some point.
Thank you. Thank you. Well, hopefully this will be published soon. So.
All right. Thank you. Take care.
Bye-bye.